All right, hello everyone. It's 1 o'clock. Everybody ready to get started? Yep, okay. So last class we started talking about the limit and how it's a fundamental concept, in fact, the foundation of calculus. And I just want to start out with this little statement here, just to remind you of the major point of today. And that is, if we're given a function and we're given some value of x, then in previous classes, all we did was plug that value into the function and it would spit out an answer. And that's all we ever really cared about. That is not what calculus is about. Calculus is about figuring out what's happening near that value that you're trying to plug in, all right? And as we're gonna see, this is gonna lead us to some very interesting ideas, and it will be the key to getting around that main motivational idea of calculus, which is how to overcome the idea of 0 divided by 0. Okay, this was what Newton and Leibniz, the two fathers of calculus, were trying to figure out. Can we get around this somehow? And it's this idea of the limit that's going to allow us to do it. Okay, so without further ado, let's get down to business. So last class, I was showing you an example of a function. This was just a polynomial function. And I said, hey, if we plug in the value x equals 2, it will spit out a point. And that's all we cared about in algebra and pre-cal. Now what we're going to do is hide that point, not care about what's happening at 2. Instead, look at what's happening near 2. And what I meant by that was that as we approach 2, so as we plug in values of x, like 1.58, it's going to spit out some y value. And we're going to be looking at what these y values are doing as these x values get closer to 2. So from the left side, you can see, or we saw last class, that those y values seem like they were approaching 8, which happens to be the value of the function at 2. But again, we don't care about that. It's what is it approaching? These numbers getting closer and closer to 8. And similarly, if we come in from the right-hand side and our x values start getting closer to 2, then again, the y values, they go up for a while. They go up past 8, but then they start coming down towards 8 again. So it looks like from the left and from the right, the function is approaching 2. I mean, sorry, the functions, as we approach 2, the function's value is approaching 8 from both sides. Is that clear? Is there anything I need to clarify on that? Okay, I looked at another example where we had a piecewise function. And so if we plug 2 into this one, and just so y'all know, I'm using 2 to plug into the function just because I had to pick a number. Okay, we could be looking at 3 or at 1 or at 0. I just picked 2 because we got to pick something. So if we plug 2 into this piecewise function, because this says x less than or equal to 2, we would plug 2 into this, and it would spit out this dot, and that's up here at 8 again. However, if we hide that point and we look at the graph to the left and to the right, we noticed last class that approaching from the left, we do approach, as we approach 2 from the left, our y values are approaching 8. But if we come in from the right-hand side, our y values do not approach 8. They actually go up to about 5 or about 5.5, and then they come down and they look like they're approaching, I don't know, would you all say 4? Looks like they're kind of coming down back to 4. So from the left, it's approaching 8. From the right, it's approaching 4. And at 2, the value is 8. Okay, so let me just restate that. From the left, that's a calculus thing. The function's approaching 8. From the right, that's a calculus thing. The function is approaching 4. And at 2, that's the algebra thing, the value is 8. All right, so those are 3 distinct things we're kind of looking at. Any questions on that?
No, sir.
Okay, good, thank you.
Actually, real quick, when it's approaching from the left, I know it's negative, and from the right, it's positive, but what did you call it when there's no positive or negative sign? Like it
Okay.
just x approaches 8, but there's no positive or negative sign.
I'm not sure I follow
Oh,
you.
you mean like it approaches from both sides? Is that what you mean? If it doesn't have the plus or the minus, are we there yet?
No, we're not there yet. We're
Okay,
not
never
there
mind.
yet. Yeah, I have not introduced any notation yet for this. Just trying to get you to understand the idea. So Brian, I'm having a little trouble understanding your question with the plus or minus.
I think I went a little bit too ahead of the homework, but never mind.
Okay, that's probably what it is. We'll get to all that notation in a moment. Okay, so now we have a new graph for us to look at. And so now we have another piecewise function. Okay, it's 3 pieces. We've got 3 pieces here. And so if I asked you the algebra question, what's the value of this function at 2? You would say, okay, well, if x is 2, then I can't use this because this is what I use when x is less than 2. I can't use this piece because that's what I do when x is bigger than 2. But when x is equal to 2, the function just spits out the value 6. So we just plug in 2, there's 6, right? Now, if we cover that up and we ask the calculus question, we can see that as we approach 2 from the left, do you see what the function is approaching? Ryan Medina, as I approach 2 from the left, what does it look like the y value is approaching here? Is Ryan here?
Yes, all right. 8?
It does. It looks like it's approaching 8, right? It's like 7.1, 7.5. Oh, I went too far. Okay, so it looks like it's approaching 8 as we come in from the left. How about, is it, oh, this is Adair? I'm going to say that. Did I say that okay? Adair?
Yes. Mhm.
Okay, Adair. How about from the right-hand side? If I start approaching 2 from the right, here it comes. Can you tell from this what it looks like the y value is approaching?
Seems to be approaching 4.
It approaches 4. Okay, so now we have this scenario. From the left, it's approaching 8. From the right, it's approaching 4. But at 2, that's the algebra, the value is actually 6, right? So none of those match up. Left 8, right 4, at 2, it's 6. Okay, so these are just the nature of these functions, is that weird things can happen. All right, here's another one. This function right here, 2 minus x over x squared minus 4. Just for the sake of doing it, what would happen if we plugged 2 into this function? So let's see. We go 2 minus 2 over 2 squared minus 4. We would get 0 on top, and on the bottom, 4 minus 4 is 0. Ah, we have 0 over 0. That's a problem, right?
Can't do it.
That would mean that at 2, if you try and plug 2 into this, the function is undefined. Okay, it's not defined. It's impossible to plug 2 in. 2 is not in the domain of the function. So when we look at what's happening at 2, there's nothing. There's no solid dots at 2. However, if we were to close off 2 and look at what's happening on the sides, can you all see that as I approach 2 from the left, can you see that it looks like the y value is approaching something? Right? Now it's kind of hard to say what it is. Maybe it's like 0.25 or negative, sorry, negative 0.25. Looks like it's about negative 0.25, right? From the left. And then from the right, let's see what happens. From the right, my y value, these are my y values right here in the black right here. It looks like it's approaching again negative 0.25. Do y'all agree with that? So this is another scenario. From the left, the function is approaching negative 0.25. From the right, it's approaching negative 0.25. But at 2, it's undefined. And at 2 is where we have the 0 over 0. So this is gonna be the one that is interesting to us. At the end of the day, this is gonna be the type of problem we are most interested in, because we can't plug in 2, but we can still see that to the left, a little to the left of 2 and a little to the right of 2, the function is giving us something. It's giving us, it looks like it's approaching negative 0.25. All right, I hope that makes sense. Okay, here's another one. Sine of x over x. And this time it's hard to see it here, but we're looking at what's happening at x equals 0, not x equals 2. Okay, so let's see. At x equals 0, let's try and plug 0 into this function. So that's going to be sine of 0 over 0. And sine of 0 is 0 from pre-cal, and 0 over 0 up. We've got this again, right? So if this were an algebra or pre-cal class, I said, hey, plug 0 into that function, you would tell me it was undefined, right? But let's look at it from the calculus perspective. From the calculus perspective, we are looking at what's happening to the left and to the right. And from the left-hand side, let me see, Vivian, is Vivian around?
Yes.
Okay, so can you tell if I start moving, I'm approaching 0 from the left-hand side. Can you tell what the y value looks like it's getting closer to?
It looks like it's getting closer to 1.
1, yeah, it's 1. And then Vivian will stay with you. How about if I come in from the right-hand side?
Still 1.
Still 1, right? So
Yeah.
again, this is another example where from the left side, it's approaching 1, right side, it's approaching 1, and at 0, it's undefined. We have the 0 divided by 0. Okay, can I clarify anything? Are we good? All right. Okay, now, ooh, okay, so this one's weird. So I'd like for us, for this one, again, to look at what's happening at x equals 0. So let's just try and plug it in first. If we plug 0 into this function, the function is sine of 1 over x, so sine of 1 over 0. But wait a minute, 1 divided by 0 is undefined, right? So the function is undefined at 0. Now you can't tell, but if you try and plug 0 into this graph, let me see if I can zoom in. My computer's having a problem. So this thing is like wiggling. And if you try and zoom into what's happening at 0, you can't tell. But you have to trust the algebra. At 0, it's undefined, right? So there's no dot at 0 anywhere. Okay, so let's see. What's happening if we approach from the left? We approach 0 from the left. Where is it? There it is. I need to zoom out a little bit. There we go. So as I approach to, look what's happening. Just keep an eye on the y value here, okay? Here we go. It goes up to 1, but wait a minute, it's going to go back down and then back up and back down and back up and back down and back up. Is that approaching a specific value or is it fluctuating?
Fluctuating.
It's fluctuating, right? And so from the left, I can say that it's not approaching a specific number. It just keeps going back and forth, right? We have not seen this yet, right? We have not seen something like this. It's always done something, right? It's always gone to a single point. Here, it just keeps oscillating. And if I try and do it from the right-hand side, the same thing's going to happen. Come in here, and then it starts freaking out. It starts going up, and then it's going to go down. It's going kind of slow, but the closer I get to 0, the faster it's going to start to fluctuate. And that's why the computer graphs it, and it almost looks like it's like a big mess in here, right? It's a big mess because the computer's having a hard time graphing all these fluctuations. So this is an example. This is a weird example. This is an example where at 0, it's undefined. From the left, there is no number we're approaching. And from the right, there is no number we're approaching. It's like all the worst scenario, like worst case scenarios possible. Does that make sense?
Yes.
Okay. All right. So here's another function, and we're going to be looking at x equals 0. So hopefully everyone's clear with the idea that if I try and plug 0 in here, right, it's undefined. And if we graph this function, here's what it looks like. It goes like this, and then it goes like, this is one of those functions from our catalog of functions, the toolbox that I said you should know what these look like. This is one of those, 1 over x. Okay, so everyone agrees at 0, we're undefined, right? That's the algebra question. All right, so now the calculus question, and it's going to Gabriel. So Gabriel here?
Yes.
Okay, Gabriel. My question is, as I come in and start to approach 0 from the left, here I come. What happens to the y value?
It's
So we're-
going down, it's getting more negative.
It's getting more negative, right? And the closer I get to 0, the more negative it's going to be. Would you agree?
Yes.
And so isn't that, what would we say? That's taking off, it's kind of headed to where? What's that kind of number way down there?
Negative infinity.
Negative infinity. Okay, now infinity is not a number, okay, it's an idea. But the idea here is that as we start to come in from the left-hand side, this graph starts to dive down to negative infinity, right? Now, Gabriel, you did great with that. So how about if I come in from the right? Does it dive down to negative infinity?
No, it's gonna go towards positive infinity.
That time, yeah, so from the right-hand side, it's headed to positive infinity. Okay, so let's recap. At 0, it's undefined. From the left, it's headed to negative infinity. From the right, it's headed to positive infinity. That clear to everyone? Now, everything we're doing right now, we're basing all of this on a visual interpretation of the graph, right? We're looking at the graph, we're interpreting that. We are going to get to a point in the next section where there is no graph. All you get is the function. And you have to figure out what the limit is, what's happening as you come in from different sides. So we'll do that in 1.4, but for now, this is where we are, right? Okay, how about this one? I'm just gonna go straight to it. We're looking at x equals 0. So let me see, Daniela? Not Danielle, Daniela Silva.
Yeah, I'm here.
Okay, Daniela, take a look at this one. What is happening at 0, Daniela? So if I ask you to plug 0 into this function, what would you tell me?
The function will be undefined.
It's undefined, okay. Now, Daniela, what happens if I start approaching from the left? If I approach 0 from the left, where's the function headed? Where does it look like it's headed?
To positive infinity.
Positive infinity. And how about if I come in from the right towards 0?
And the same, like
Same thing, right? Same thing. So in the last problem, the left side, as we came from the left, it went down. From the right side, it went up. This problem, from both sides, it's going up, right? Like that, headed to infinity from both sides. At 0, undefined, but from the left and right, it's headed to positive infinity. Good. Okay, now with all of that covered, let me zoom this out a little bit so it's easier to read. Now remember, all these notes are online, you can get to these. So says here, basically when we find the limit of a function at a point x equals a, we are inspecting the behavior of the function near a, right? We're inspecting the behavior of the function near a. We do not care about the actual value of the function at a. We don't care, okay? It's what's happening near it. When we inspect the behavior of the function at x equals a from the left or the right-hand side, right? We're gonna look at both sides to see what's happening. When we approach one of the sides, one of these three things can occur. Either the function approaches a single number, okay, that would be like on these that we did, right? As we came in from the left, it looked like it was headed to 8. From the right, looked like it was headed to 4, right? So it can either go to a number, it can oscillate infinitely many times. We saw that with that weird one. Or the function can approach positive or negative infinity. Those are the only three outcomes. When you're looking at a limit and you're coming in from one of the sides, it's either headed to a number, it's oscillating for like infinitely many times, or it's going to head to positive or negative infinity. Okay, those are the only outcomes that can happen. Remember, and I keep saying this, you know, we don't care what's happening at A, okay? I don't care at all. Now, some language, okay? So whenever we're going to look from the left, okay, whenever we're looking and we're inspecting it from the left, we call that the left-hand limit. Makes sense, right? Left-hand limit, you're coming in from the left. And when you're inspecting it and looking from the right, we call that the right-hand limit. So that's just language now. If I show you a graph right now and I call on somebody and I say, hey, what's the left-hand limit? You should know, okay, that means I need to look from the left and come in and see where it's headed, right? Now we have notation. So this is now the new thing, the notation. How do I tell you as a student to take a look at this function and approach this certain value from a certain side? How do I, other than writing it in words, what's the mathematical notation we use? And it's here, but I'm going to rewrite it. So remember, you're given a function, right? So you're given some function. And if I want you to inspect that function near some value and come in from the left, here's how I'll write it. I'll write lim, which stands for limit. Below the lim, I'm going to write x with an arrow to a. And that's telling you, hey, you need to look what's happening as x gets close to a. And then I'm going to put a little negative sign on the top right-hand side of the a. And the negative sign means, like if you think about a number line, here's 0, positives are over here, negatives over here. So the left-hand limit, the negative sign helps you remember you're coming in from the left, okay? Because the negatives are on the left. Okay, and then I have to write f of x. So this says, take a look at this function f of x. Approach a from the left and tell me what's happening. And then you're going to have one of three things happen. It's either going to give you a number, it's going to oscillate, or it's going to be infinity or negative infinity, right? Those are the three outcomes. Now, if we want to do the right-hand limit, the only difference, as you might suspect, is that instead of using a little plus sign there, why is that not working? Okay. We change that to, I'm sorry, instead of using a minus sign, we use a plus sign, and that would be for the right-hand limit. Is that clear? So if you see a little minus, you're checking from the left. If you see a little plus, you're checking from the right. Now, when we want to evaluate limits, okay, and look at approaching a from both sides. So if I want you to actually look and do an inspection from both directions, positive and negative, the notation for that is that I won't put a plus or a minus. Okay, so I'll do lim, I'll go x approaches a, and then I'll put the function f of x. So you see there's no plus or minus there? No plus or minus means you need to check both. Okay, so it's implied that it's both the left and the right. Any questions?
No, sir.
Okay, let me see here. So let's look at this notation here. I'm going to zoom this in. Okay. So Axel, is Axel here?
Yes, sir.
Okay, so Axel, do you see this notation right here?
Yes.
I'm going to write it up here again. Can you just tell me, like in words, what this is telling you to do?
It's asking me to look at, to go towards 2 from the left side.
Okay, and by looking at this graph, Axel, can you tell me what the answer would be?
It would be at 8.
It'd be 8, right? So if you just take a dotted line and just draw it straight up through 2, then you're basically walking along this function headed towards x equals 2 from the left. And Axel is saying that it looks like we are approaching a value of 8. Now, we did that problem earlier, but now the notation matches up. So what we would say is the answer to this is 8. Okay, so do you see why that is, the way we write that? Okay. Now, the next one, here it's saying, take the limit, let x approach 2 this time from the right. And so are we clear why the answer is 4? right? We're coming in, here's 2, and we're going to come in from the right. So we're walking along this function. We're getting closer and closer and closer. Wait a minute, hold on. Benjamin, are you there?
Yes.
Okay, so Benjamin, I'm coming in from the right, right? I'm walking along here and I'm walking. But when I actually get there, there's a hole. So why is my answer still 4?
That's where the limit is, but if it was 4, it wouldn't be a function then, right?
Kind of, I guess.
Do you have like open parentheses for maybe?
No, what I'm trying to get you to see is that this, when we say limit, right? I'm telling you to approach 2, right? From the right. The fact that there's a hole here shouldn't mean anything to you.
So it's
Why?
still 4 then.
Yeah, it's still 4. It doesn't matter that there's a hole because the hole is what's happening at 2, right? At 2. So we're actually supposed to act like this isn't even here. Like we're just ignoring everything that's happening at 2. And we're only concerned about what's happening near it. Okay, so the fact that there's an open hole changes nothing in terms of our answer being 4 still. Okay, everyone clear on that? That's very confusing to students because they see the hole and then they want to say that, you know, it's okay, then it, you know, there's a hole there, so it can't, the limit can't, you know, possibly have an answer or something. It's okay to have an answer because it's what's happening near it. All right. Javier, are you there?
Yes, yes, I'm here.
Okay, so Javier, this one right here, this notation, limit x approach 2 of f of x equals 8. What is this saying we're supposed to do?
It's telling us we're supposed to look at the function and approach and look at both sides as they're approaching 2.
That's right, both sides. And why, Javier, is the answer 8 then?
The answer is 8 because as you can see, like on the left side, you can see it approaches the y value 8.
Okay.
And from the right side, it also approaches 8.
That's right. Okay, so from both sides, it's headed to the same place, right? So the answer is going to be 8. Good. All right, so some more terminology. We call the left and right hand limits one-sided limits. And that should make sense because both the left and the right means you're only looking from one side, right? From one direction. When we don't put the plus or minus, that implies we are looking from both directions, right? Now, in order for us to say, like in this problem here, for us to say that the answer was 8 meant that it had to be the same from the left and the right. If one of these was different, then we would have to say that this is not 8. Okay, and I'm going to give you a visual example of this, but this is to tell you, this note is to tell you, what do you do when you're looking from both sides and they go to different places? What do you write down? And what we write is the words does not exist. We will say the limit does not exist. If the left limit and the right limit do not match to the same number, then we say the limit doesn't exist. Or we'll write DNE. Okay, that's the other, this is an abbreviation, DNE. Most textbooks use that. You'll see me write that all the time. DNE, does not exist.
Would that apply to that one problem we had earlier?
Which one?
The piecewise function, yeah.
This right here. Okay, very good, Benjamin. So right now on this problem, if I asked you, Benjamin, for the limit as x approaches 2 of this function, that means you have to check both sides. So you check from the left, it's headed to 8. You check from the right, it's headed to 4. Those are different places, right? So you would tell me that this limit does not exist. Okay?
Okay.
Now this answer is 4. The reason why this answer is 4 is because there was a plus there. So you're only looking from the right. And from the right, it's headed to 4.
Okay.
Make sense?
Yeah, you're pretty much setting like a limit on it, kind of.
Yeah. So this, when you don't have plus or minus, that's like the most strenuous case because you're checking both sides and both answers have to be the same for it to exist, for the limit to exist. Okay, so it does not exist. All right, so in this is exactly what Benjamin was just saying. From the left, it's 8, from the right, it's 4. And so the limit as x approaches 2 of this function doesn't exist. Okay, this one's a little more interesting. Yeah, okay. So we did this one earlier. Do you remember when we did this? And it looked like from the left, it was headed to negative 0.25. And from the right, it looked like it was headed to the same thing, negative 0.25. So if I ask what's the limit as x approaches 2, that means you have to check both sides. The answer would be negative 0.25. Does it matter? Does it even matter that at this value of 2, does it matter that it doesn't exist, that there's a hole? That has no impact on the limit, okay? The limit doesn't care what's happening at 2. The limit only cares what's happening near 2. So this is still a legitimate answer. All right, now, suppose f of x is defined near a, and we write this down, right? So we're basically saying whenever we write this limit, I'm going to write it a different way because I don't like the notation. If you ever write this down, if you're going to say that that this limit is equal to L, which is going to be like a number, then what we're saying is that as you approach x from both sides, the closer you get to a, right? The closer x gets to a, the closer the function gets to L. The closer x gets to a, the closer the function gets to L. I'm going to go back up to this one right here. This one right here, the limit was 8, right? That means the closer you get to 2, the closer the function's value gets to 8. It has, whenever you write a limit, and I can't stress this enough, it does not matter what's happening at a, okay? You need to just get that out of your mind. It's not what calculus is about. We're not worried about it. We're only worried about near it. Okay. Now we're going to do something a little different. Instead of me giving you a picture to look at, I'm going to give you a couple of conditions and ask you to draw a picture, draw a function that satisfies these conditions. Make this a little smaller. Okay, so we are supposed to sketch a function that satisfies all 8 of these conditions. Now, everybody's graph is going to look slightly different, but we all should have the same 8 conditions met. So let me show you how you do this. Just going to throw a little graph over here. I guess that's all I'm going to get in there. All right, so let's start looking at these conditions. First condition. That says the limit, I'm going to write it up here just so it's clear. Limit as x approaches -2 of this function that we draw has to be 3. Okay, so that means, let's see, Matthew, is Matthew here?
Yes. Yeah.
Okay, so Matthew, if the limit as x approaches -2 of the function, if that has to be equal to 3, that means that when I draw my function and I go to -2 here, what has to be happening on the graph?
From the both left and right sides, they need to be approaching 2. -2.
Approaching
-2.
That's where, okay, so we're approaching -2 from the left and the right, but what is the y value of the
It'll be
function?
3.
3,
It'll
okay.
be 3.
3. So 1, 2, 3. So tell me this, Matthew, could I write this down? Could I draw like a little open circle and then like a little curve coming off of that and a curve coming off that? Matthew,
Yes.
would you agree that if I drew it like this, that would satisfy this first condition? From the left, it's approaching 3, and from the right, it's approaching 3.
Yes.
Yes, everyone else agree with that? Okay, and I don't have to use squiggly lines. I could have used like a straight line. It doesn't matter. as long as it's a function. And remember, to be a function, you have to pass the vertical line test. So just make sure that whatever your picture looks like at the end passes the vertical line test. Okay, now, Matthew, I could have put a dot in here too, right, Matthew?
Yes.
Yes, until we read the second condition. Right? Look at the
Yeah.
second condition, everyone. The second condition says that what? So, Emmanuel? Is Emmanuel here?
Yeah, I'm here.
Are you following?
Yes.
Okay, so what is the second condition telling me I need to do, or telling us we need to do here?
So when x equals -2, it will be at 0.
That's right. And that's an algebra thing, isn't it? This is not a limit. This is just telling us when you plug -2 in, the graph should spit out 0, right? So
Yes.
like this. Okay. And so does everyone see that when Matthew did the first condition, he said, yeah, we could fill in that dot. I agree with him until we get to the second condition, which means we can't put a dot in there. Do y'all see why we can't have a dot in both places? Then it would
Make it
fail
not
the
a
vertical
function.
line test, right? You would have, if you try and draw a vertical line, you're going to hit the graph in two places, and that wouldn't be a function. So you have to eliminate one of those, and that means you have to eliminate the dot here, because this dot has to be here. Any questions?
I have a question not about like number 2, but what happens if like y equals y equals 1? How does that work for limits then, or like a vertical asymptote?
Wait a minute. What if y equals 1?
Yeah, how would that work with the limit? Like if you had like an equation like that, would the limit be 1?
Oh, okay. So you're just saying, like, if you have a horizontal line,
Yeah.
like, okay, so you're saying if you have the function like f of x equals 1 or y equals 1, then that would just be a horizontal line. Yes?
Yeah.
Then the limit to, you could go to any point. It wouldn't matter where you go, 2 or -2, and no matter what, if you were to take and approach from the left or the right, doesn't matter where you're going, because this is a constant function, your answer would also be 1.
Okay.
Because your y value is just always the same.
Now I
Is
was
that what
curious.
you were asking?
Yeah, and I was curious about like vertical asymptotes too, like so like 1 over x.
Mm-hmm.
Would be approaching infinity at one point.
That's right. So if we were to do the graph, 1 over x, which looks like this, if we were to ask for the limit as x approaches 0, let's say from the right of that function 1 over x, then we are going this way. And I forget who did this one earlier, but I think it was Daniela, told us that that was headed to infinity from the right. So our answer here would be infinity.
Okay.
Okay.
All right. Thank you.
Okay, no problem. Let's continue with these conditions. So the next person up is Gage.
Hey, Professor.
Yes.
I apologize. It's a pretty dumb question, but when we do the number 1, right? So why did we have to draw from left and right, since we're just looking from the left side, since it just says x limit as -2?
Okay, so I did this on purpose to see if I could trick you. This is the number -2, right? If I wanted you to come from the left, the negative sign would have been up here to the top right of the number.
Oh, I see.
that?
Okay.
So because there's not a plus or a minus on the top right, that means you have to check from, it has to be that from both sides.
Got it.
But I put -2 there to try and trick people to be like, oh, wait, that should be from the left. That has nothing to do with it. We're approaching the number -2 from both sides. So great question. I'm glad you asked, because the intention was to try and confuse you so someone would ask that question. Is that clear for everyone? Yeah?
Yes, sir.
Okay, so we got the first 2 conditions done. All right, and Gage, no, wait. Gage? No.
Yes.
Did I call you Gage? I thought I put it next to you. Yeah. All right, so Gage, how about this third condition? I'll write it down up here. Limit x approaches 1, there's a little negative sign there, this function. needs to be -1. So Gage, what do you want me to do here?
Okay, so
Where are we approaching? What X value are we approaching?
1.
Okay, are we approaching it from both sides, left, right?
Just the left side.
Okay, and when we approach from the left, where should our function be headed?
Was it -1?
-1. Okay, so how about I do this? I'm going to go down 1. Here's -1. Down 1. I'm going to put an open circle here because I don't really care what's happening at 1. But from the left, I have to be headed there. So how about if I just like do that? Do you see how I just like connected to this little circle? I just connected this left side. So now everyone agree that if you were walking along this function, you would be approaching -1 from the left?
Yes.
Could someone have done this instead? Is this still, as you come in from the left, is it still approaching -1?
Yes.
Yeah. So everyone's graph's going to look a little different perhaps, right? Okay. Good job, Gage. Next person, Austin.
Yes, sir.
You get condition 4, which is limit x approaches 1 plus sign f of x equals 2.
So as we come in from the right side towards 1, we're going to be approaching 2.
2, right? So how about we go up to 2, like here's 1, we go up to 2, we draw a dot or open circle here, and then just come in with anything from the right, right?
Yep.
I'm going to do this, okay? So as I come in from the right, I am approaching 2. Now, Cody,
Yes.
next condition tells me to do what?
At 1, it's the x or sorry, at when x is equal to, apologies, it sets it to 1, 2, I mean.
Yep. So that means I'm going to do what to my graph?
It means you're going to put a dot at 2.
Yep. When you go to x equals 1. So we're actually going to fill this dot. We're going to fill that dot in because at 1, we're supposed to spit out 2, right?
Yes.
I'm going to highlight the 2 things. These 2 in yellow have been the algebra parts of what we have to do, right? And what's in green has all been calculus stuff coming in from certain sides. All right. Who was that just answered me?
Me.
Cody? Okay.
Yes.
I thought I called Austin. Did I call Austin already?
I did 4.
Oh, you did 4. Okay, sorry. All right. So how about Gene?
Yes.
You got 6.
You would, while approaching 4 from the left side, it would equal infinity.
Okay, so let me write, here's 2, here's 3, here's 4. And as I approach 4 from the left side, you said I need to go where?
To infinity?
So that would look like what from college algebra? What type of function did that as you came in and it just kind of took off?
Yeah, one of the asymptotes, right?
Yeah, it's like a vertical asymptote. That's exactly what it is. So I'm going to put a dotted line here, which is not part of the graph. And what I'm going to do is I'm going to say from the left, as I approach 4, I know that this side has to go up towards infinity, and I'm going to just draw an arrow. And that satisfies this 6th condition, that as I approach 4 from the left, the function heads to infinity. Good job. All right.
Thank you.
Mustafa, you're up. You've got the 7th condition. Is Mustafa here? No? Okay. All right. Fiona?
Yes.
Okay, Fiona, you get the 7th condition.
So as x is approaching 4 from the right side, it hits 0.
It hits 0?
Oh, it doesn't. It approaches 0.
It approaches 0, right? So
Okay.
when I do that, I'm just gonna, I don't know, I could bring it in like this. I could bring it in like this. It doesn't matter which way I bring it in. I just know that I need to be approaching 0. And when I actually get to 4, because I don't know what's happening there, I'm just gonna put an open circle there. Fiona, is that okay? From the right-hand side approaching 4, we are headed to 0, right? Okay, good. Now, last condition goes to Brian Hernandez.
Wouldn't it not exist on the graph?
Yeah, exactly, right? So this is just telling us that f of 4 is undefined. So had Fiona told us, you know, hey, go ahead and just put a dot there, if she had said that, then condition 8 would have said, wait a minute, hold on, erase that. Because you can't have a dot there, because it's supposed to be undefined. Does that make sense? Okay. So I'm going to take that out. Now, that's it. We've satisfied all conditions, haven't we? Now we need to finish it, because right now this is not a function, just a bunch of cluttered crap everywhere. So what I'm going to do is connect all my pieces together. And I'm going to start from the far left, and I'm just going to have my artistic freedom here to connect things together. Do you see how I did this? I just kind of connected everything together to make it look like a function. And I'm also making sure I pass the vertical line test. So no matter where I draw vertical lines, I'm never going to hit the graph more than one time. So it does qualify as a function. And that's it. I've drawn something that satisfies all those criteria. So everyone's going to have a slightly different picture, right? Any questions on that?
I thought we were gonna separate it.
Okay. All right. Let me see here. I want to look at something real quick. Now, this section 1.3 in the textbook, they do something that I'm not a big fan of, but we're gonna do it just so when you get to your homework, you'll know what they're talking about. Okay. They want you to start thinking about how you would deal with limits if you're not given the graph. Okay, so at the end of this section, that's what they're going to have you start doing. So I'm gonna give you a problem like that. That way, when you do your homework, you'll be okay. So what if I asked you, you know, what's the limit as x approaches 1 of x squared minus 1 over x minus 1? All right, so no graph. You don't get a graph, okay? So I'm going to call on somebody now. Danielle?
Yeah.
Okay, so if this is telling you, right, Danielle, that you're supposed to figure out what this function's doing as x gets close to 1 from both sides, right?
Mm-hmm.
But you don't have a picture.
Mm-hmm.
So if we can't use a picture, then couldn't we just kind of like think of our own points close to 1 that we could check to see what's happening?
And make a T table?
Like a table, right? Good, exactly. So the idea is this, everyone. We don't know what the graph looks like, but what we know is we have to approach 1 from both sides. So I'm just going to make a table where I'm just going to plug in some values of x and then just see what this function spits out. Also, Danielle, I didn't mention this, but maybe everyone saw this. What would happen, Danielle, if we actually plug 1 into the function? Like if I try and plug 1 in here, what happens?
And to all of it, it would become undefined because there cannot be a 0 in the denominator.
Yeah, so does everyone see that when you plug 1 in, it's undefined, right? But this is a limit, so we don't care what's happening at 1. So we're going to pick some values that are close to 1, and let's start coming in from the left side. So Danielle, I'll leave you alone in a second, but can you give me a number that's kind of close to 1? On the
point
left of, to the left
on
of
the
one.
left side, to the left of one would be like, wait, to the left of one? Like negative number?
No, no, look at your number line. Here's 0.
Oh, we're approaching 1. Oh, okay, like 0.1.
0.1, okay, that would be pretty far over here, like 0.1 here.
Ah, oh wait, that's
Get
the
closer.
0. My bad. Oh, like 0.99.
Okay, so 0.9, do y'all agree that's close, I guess? So I could try plugging in 0.9. Okay, Danielle, give me one even closer.
Like 0.99.
Okay, 0.99, do y'all agree that's even closer? And then I could go even closer, 0.999, right?
Yeah.
And I think that's good enough. Okay, so what we'd have to do now is we'd have to get on our calculators and we would have to plug that into this. So I'm only going to do one of these, all right, because this is tedious. I'm going to do the 0.99 one. So I'm going to take this and I'm going to plug in 0.99. 0.99, I've got to square it, subtract 1, and then I've got to take 0.99 and minus 1. And I get on my calculator and I do this. I hope I did all that right. I get 1.99. So I'm going to let you do that on your own to make sure you can get that answer, but I get 1.99. Now, if you do the other ones, here's what you're going to get. You get 1.9 if you did this one, and this one you get 1.999. Okay, just trust my answers there, okay? So Danielle, I'll leave you alone. Let's see, Laura.
I'm here.
Okay, Laura, my question is, from what we just did, it looks like each of these numbers, 0.9, 0.999, 0.99, 0.999, those are all getting closer to 1, aren't they, from the left?
Mm-hmm.
What does it look like the Y values are getting closer to?
It looks like they're approaching 2.
It looks like they're approaching 2, right? So it looks like our left-hand limit is 2. But we also need to check the right-hand limit. So Laura, what could I use here in my table to check the limit from the right? So give me numbers, give me a number that's close to 1, but on the other side.
1.1.
1.1, how about even closer?
1.01.
Closer.
0.001.
You see, you get the idea, everyone? And then what you could do is you could start plugging those into the function. And if you did it, I'm not going to do it, you get 2.1, 2.01, 2.001. And can you all see that if you did this, those also look like they're approaching 2? They're just getting closer and closer to 2, right? So we would conclude from this that this limit is equal to 2. So when they, in the textbook, what they do is they give you this, and then they tell you, this is the way they write it. They write something like this. X equals, let me try and match what they do here. Plus or minus, you know what? No, that's not right. Well, they'll give you a list of numbers to check. How about, I'll just say that. They'll give you a list. So they're basically telling you what numbers to plug in here. And then you just plug them into the function, use your calculator, and see if you can see a pattern of where it's headed. Does that make sense? Okay, that's not super critical in this class. Like, I'm not going to test you on this, but in your homework, they want you to do it. All right. Okay. While we're talking about this and we're about to transition into the next topic, I thought it might be a good time to give you something kind of random and useless, but kind of cool. So if I take the number line, and let's just take the numbers between 0 and 1, okay? I'm going to ask Austin. I know I already called on you, Austin, but I just had a feeling you're going to have a good answer for this. So Austin, can you think of what, well, if I ask you, what is the number that's right next to 1? What would your response to that be? I'm just curious. What's the number right next to 1?
Since it'd be 0.9 repeating, wouldn't it?
Like 0.99999 forever?
Yeah.
Does that seem like a really good answer? I like that answer. 0.999 forever. Does that seem reasonable to everyone that that number should be the number right next to 1? Yeah.
Isn't there like an infinite amount of numbers until we get close to 1? There's, right?
Yeah, so the big question here would be, my question, I guess, back to Austin would be, so you're telling me that there's no number in between here and here, like, because if there was a number in between these, then that would be a number that's even closer, right?
Right.
Right, okay. So this should be the one right next to it. All right, so just hang with me here for a second, all right, everyone? Let's just follow me and see what you think of this. So here's what I want to do. You just tell me, stop me at any point if you just don't believe what I put down on this page, all right? So first thing I'm going to write down is let x be equal to what Austin said, 0.999 forever. All right, so I'm defining x that way, all right? Everyone happy? X is that. Now, I would like for us to then be able to conclude or say then 10 times x. Well, what happens when you multiply a decimal by 10? What happens to the decimal point?
Moves over 1 place.
Moves 1 to the right. So do you agree then that this should be 9.999 forever? Anyone disagree? We're all happy?
Yeah.
Right, multiplying any number by 10 moves the decimal point 1 place to the right. Okay, now, next thing I want you to tell me is whether or not you agree with this. If I take 10 x's and I subtract 1x, how many x's do I have?
9.
Just algebraically.
9.
10 apples, take away an apple. How many apples do I have? 9, right? So does everyone agree that 10x take away an x should give you 9x? Right? But take a look at this. Going back up to what I defined x to be, 10 times x would be 9.999 forever. And if I subtract from that x, which is 0.999 forever, what would that equal? So think about what would happen if you took 9.99999 forever and subtract 0.999 forever. I'm going to ask Austin because he came up with 0.999. Austin, what would happen if you subtract these? What would you be left with?
I want to say just 9.
Yeah, just 9, right? It's kind of like all these decimals that go forever kill each other off, right? So you just get 9. But what does that mean we're saying here? 9x has to be 9, right? 9x would have to be 9, which means x has to be what?
1.
1. But x is this. So what I just showed you is that the number 0.9999 forever is not the number right next to 1. It actually is the number 1. It's weird. There is no number in between 0.999 forever and 1. They are the same number. Very strange. Very strange.
Why do we
So,
write that?
what's that?
So why do we write 0.999? Like, what's the purpose of it?
Well, I think when you write it, you don't realize that this is the way the numbers work, right? Like, this is actually a pretty profound consequence of our number system. So now if I ask Austin the question again, all right, which I'm not going to ask you, Austin, but now as a whole class, what is the number right next to 1? the correct answer is there is no number right next to 1. It's impossible to find the number right next to 1. So let's say that someone comes up with a number. Okay? Let's say someone says, here's my number. I'm going to call it A. And they say, that's the number right next to 1. That's it. Here's how I could prove them wrong. All I have to do is take that number A, add 1, and divide by 2. So basically what I'm doing is I'm taking the number they think's right next to 1. I'm adding this number, and I'm dividing by 2. So in other words, I'm taking the average of the two numbers. And anytime you take the average of two numbers, you'll always get the number in the middle of them. So what I would do is I'd create a new number that's even closer. And then that can't be the closest one because I could always take that one and then take 1 and take the average, and I'd have another number closer. So there is an infinite number of numbers next to 1, but there's not one right next to it. It's really kind of a mind-blowing thing. Just how many numbers are in this number line. There's an infinite number of numbers, but it's a crazy type of infinity, and I'll get to that later. I'm not going to do it today because I've already taken enough time. It turns out that there's 2 types of infinity. Okay, everyone has heard infinity, but there's actually 2 types. It's called countable and uncountable. And when you're looking at the numbers between 0 and 1, we're talking about an uncountably infinite number of numbers, as opposed to a countable infinite. But I'll get to that. Stay tuned. That'll come at some random point later in the semester. Okay, I hope that was fun. Moving on. Next section. So everything we've done up to this point, we've analyzed graphs, and we've been able to look at limits from the left and right, and everything has been pretty okay because it's visual. Now what we need to do is invest some time into figuring out how do we determine the limits of a function if we just have the function, right? F of x equals blah, right? No pictures. To do this will require significant amounts of algebra and tricks. All right. So I told y'all last week, I said calculus, the ideas of calculus are not really the thing that trip people up. It's the algebra of the calculus that gets people. And this is where it begins. All right. We're going to start to see all sorts of weird algebra come into play. And so I'm just warning you that that's where we're headed. All right. And the tricks part of it is like, I have to kind of show you how to do certain problems. And then you're going to go like, shit, I would have never thought to do that. And then I'll be like, yeah, you would have never thought to do that. But now you know that you can do that. And so when you're faced with a problem, you better remember all these little tricks because you got to be willing to try different things. So this is kind of very different than any other math class that you've had in the past, where it's very mechanical, right? It's like, okay, give me the formula. I'll plug things in, you know? This is like, no, you have to like have some sort of intuition that you start building up because you start seeing me do things. And you're like, okay, well, I saw him do that. I'm going to try it, you know? And there will be little like rules of thumb that we follow, but there's no like set template to solve every problem. Every one of them is uniquely different. All right, so here we go. It begins. All right, so we have a couple of things that we have to get out of the way that are just kind of notation and rules. So we have these things called the limit laws, and they tell you what you're allowed to do and not allowed to do when it comes to limits. And these are really confusing when you first see them because this just looks like a bunch of gibberish. But as we do examples, I'll illustrate these laws. The first law says that if you have two functions being added together and you want to find their limit, you can just do them separately. I'll give you a specific example next to this. If I'm taking the limit as x approaches 2 of, let's say, the function x squared plus some other function like sine x, that if I want to take this limit and figure out what's happening, I can look at this one, x squared by itself, and sine x by itself, figure out the answers for each one of those, and then add those two answers together. So it allows me to break the limit up into two limits. See how that works? The limit of a sum turns out to be the sum of the two limits. That is a law, you're allowed to use it. The next law says, well, if you have subtraction, you can do the same thing, break it into two. The next one has to do with constants. This law says if you have a constant, C, in front of a function, and you want to take the limit, you can ignore the constant and just do the limit of the function and then multiply the constant. I'll give you an example. So let's say I'm trying to figure out the limit as x approaches, let's say 5 of 3 sine x. This law says I can ignore the 3 and just do the limit of the sine function. Okay, so the 3 can come out here. I can figure out what this is. And once I figure out what that is, I'll multiply it times 3. So constants can be factored out. That's what this is saying. Constants can be pulled out of limits. Questions? Okay, next one. If you have two functions that are being multiplied and you're trying to find their limit, you can look at each one individually and then multiply those two answers. Example, if I want the limit as, let's say, x approaches 0 of x squared times sine x, I am allowed to look at the limit as x approaches 0 of x squared and then do the limit as x approaches 0 of sine x, figure out what each one of those is separately, and then multiply those two answers together.
Aren't these like the same rules like as logarithms? Kind of.
Well, logs are weird because if you have like the log of a product, it turns into the sum of logs. This is not the same because products, see, this is a product right here between those two. The product still turns out to be a product. Like it doesn't turn into addition. It still stays a product.
Oh,
This is just saying that you can focus on the two functions individually, that you're allowed to do that. Because it's not given. I mean, we should never assume that that would be true, but it is. The next limit law says that if you have two functions being divided, like if you take a function divided by another and you want to know the limit, you can do the limit of the top one and bottom separately. So it just allows you to look at them by themselves. And then whatever answers you get, you divide those answers. The next limit law says that if you are trying to find the limit of a function raised to a power n, you can first figure out what the limit of the function is and then raise that answer to the power. So in other words, if you have something like this, let's say we had sine x to the 7th power. You don't need to worry about the 7th power. You can just figure out what the limit as x approaches 0 of sine x is. And then whenever you get that answer, raise it to the 7th power. So you can put the limit inside of a power and deal with the power afterward. That's what that law says. Okay, the next one says that the limit of a constant is a constant. This is what Benjamin was asking earlier. Benjamin asked, hey, what if we have a function that's constant? Then the limit from everywhere should be that constant. And that's what this limit law is saying. So to illustrate this, if I take the limit as, let's say, x approaches, I don't know, I could pick any number here, 7. And here is just the number 4. See, that's a constant. Then it doesn't matter what I'm approaching. The answer is 4 because this is just a constant. All right, the next one, 8, is very important. All right, it says that, and it's kind of so easy, it's confusing. It says, look, if you let x approach a, right, then x is going to approach a. All right, so let me see. If I take the limit as x approaches 7 of x, the answer should be 7, right? Because this is saying, hey, look, let x get close to 7. What is x getting close to? 7, right? Make sense? Don't make it more confusing than it has to be. That's just a straight, what we call direct substitution. You're just plugging in 7 right here, and that's your answer. This next one just says, same exact thing. If you throw a power on that, so let's say I were to have thrown an x cubed on here, then my answer would still be just the 7, but now cubed. That's what this is saying. And then 10 says, if you take the limit as x approaches a of the square root of x, that should be the square root of a. So same thing, if you replace that x with a, then it's just going to be the square root of that a. And then don't worry about this one. We'll get to that as we move through. All right. Now look, whenever I present these limit laws, they're always weird because you need to see them in action, but I have to present the laws first. So I presented them. If you're still confused on them, don't worry about it. We'll work it out as we work through the problems. All right, this is a very important property, the direct substitution property. So before I begin this, we want to make sure we understand what the implied domain of a function is. And I think we talked about this last week. If we write a function down, like this function right here, it is implied that x can't be 4, okay, because wouldn't that give us division by 0? And we know that x must be greater than or equal to 0 because we have a square root. So the restrictions that we have on x in order for this function to make any sense is called the implied domain. I don't have to write that down, in other words, it's implied. I think I gave you the example of y'all wore clothes, right? Didn't I do that? I said everyone wore clothes to class. It was implied that you could do that, right? So whenever you write a function down, if the domain isn't stated, there is an implied domain. It's the domain that makes the function make sense. Now, here's the direct substitution property. If the function you're looking at is a polynomial function, those were studied in college algebra. A rational function, those were studied in college algebra. A trig function, studied in pre-cal. Exponential function, studied in college algebra and pre-cal. A log function, pre-cal college algebra. All of these functions, if you're ever looking at those, then as long as the a you're approaching is in the implied domain, then the limit of the function is just what you get when you plug that number into the function. So let me give you an example because this can make no sense. What if I take the limit as x approaches 2 of x cubed minus 2x plus 1? What the direct substitution property says is that if this is a polynomial, rational function, trig function, exponential function, log function, right? Which in this case, it's a polynomial, right? Then as long as the number we're plugging in, so as long as the number we're plugging in here, oops, that didn't work. Let me undo that, sorry. As long as the number we're plugging in is in the domain of this function, the answer is just what you get when you plug 2 in here. You don't have to check from the left and right. The answer is automatic. As long as this is a polynomial or a rational function or trig or exponential or log, and as long as this number that we plug in is in the domain, then the answer is just plug it in. So for this, all I'd have to do is plug 2 in for all the x's. So 2 cubed minus 2 times 2 plus 1. This is 8 minus 4 plus 1. So the answer is 5. Direct substitution. I just replaced the x with that number. I'll give you another example. The limit as x approaches pi, that's a pi, of cosine of x should be equal to, well, is this a trig function? Okay, is pi in the domain of cosine? So can you plug pi into cosine?
Yes.
Yeah, okay, so my answer should just be cosine of pi. I don't have to do any work. That's -1, by the way. Cosine of pi is -1.
I was gonna say that.
Direct substitution. Let me give you an example where you could not do it. Limit x approaches 1 of x squared minus 1 over x minus 1. This is the problem we did at the very end of the last section where we made a table, right? This is a rational function, okay? So we should try direct substitution, but we have a problem. The problem is that 1 is not in the domain of that function, right? You're not allowed to plug 1 into this function. So you can't do direct substitution. Go ahead, try it. If you try it, you're going to get 0 over 0. And that's undefined. So the moral of the story for this direct substitution property is that we want to use it whenever we can, because it's just directly substituting a number in. It's almost like the algebra stuff used to, just plug numbers in. This isn't going to come up a lot, but when it does come up, we want to use it. Questions?
Okay.
Okay. I want everyone here to just look at those and see. I'm going to let you work on your own. I'm going to give you about, I don't know, 3-4 minutes and just see if y'all can come up with some sort of, like, you know, can you use the direct substitution here or not? That's basically the question. Can you use direct substitution? Yes or no? If you can, go ahead and do it. If you can't, just say can't use it.
Just those two problems? There's not more, right?
Yeah, just do those two for now. Just going to give you another like minute and a half. All right, I think that's sufficient time, at least for the first one. So Claire, are you here?
Yes.
Yes. Claire, on the first one, could you use direct substitution or not?
I'm gonna say yes.
So did you try plugging 1 in?
No.
Just plug 1 in for x. And you'd get 1 squared plus 1 plus 2 over 1 plus 1. And that's not going to be a problem, right?
No, it's
There's
not.
no division by 0 or anything. I think on top you get 4 and on the bottom you get 2. So the answer is 2. So the limit of that is 2. Direct substitution. Now, Braxton. Braxton here?
Oh yeah, I'm here.
Okay. So, oh, there you
I'm
are.
here.
Okay, y'all like, this one thing I don't like about Zoom, and I've sent in requests, is that there's no way to organize your video streams. So I can't like put you in alphabetical order or assign a number to you. So Braxton, like you were like in the top right-hand corner a little while ago. Now you're in my bottom left-hand corner. So I had trouble finding you. All right, Braxton, what about this part B? Can you use direct substitution here?
No, because the just equals 0 and it's undefined.
Yep. Okay, so does everyone see that if we try direct substitution, we'll get 1 cubed minus 1 over 1 minus 1, and that gives us 0 over 0, right? So no direct substitution. Now, is everyone clear on that? So the first part A, we are done. Okay, the answer is 2. The second one, part B, we are not done. What we know is we can't use direct substitution. Does the limit exist though? Do we have a limit from the left and from the right? Is this headed somewhere? That's still an open question. We don't have the answer yet. So I'm going to show you now. I'm going to graph it for everyone so you can see it, all right? I want everyone to see what that one looks like. X cubed minus 1 over 1 minus x. Okay, here's the graph. Now we were approaching which value? What were we approaching? We were approaching 1, right?
Yes.
And when we tried direct substitution, we got 0 over 0. So that basically means we don't know. But now if I look at this, and let's go to Dilpreet.
Yes, sir, I'm here.
Okay, so from looking at this graph, we are approaching 1. Can you tell me just by looking at this what the limit is?
Is it from left or right?
It's both because it doesn't have a plus or minus, right? Our thing had just limit x approaches 1 of this. And so now we're looking at that. So you have to approach from both sides. So does it look like it's headed somewhere to you?
No.
What's that?
No.
No?
I mean, it just to infinity.
We're approaching x is 1, right? So here's 1. Come down here to the graph. We know that when you plug in 1, you get 0 over 0, right?
Mm-hmm.
So the graphing, this is a website, and most graphing calculators do a terrible job of this also. There's actually a hole here. They don't show it on the graph, though. They're not showing it, but it's there.
Oh, that
So
makes
if I come in from the left, am I headed somewhere?
2, I mean, 2, 3, negative.
Negative 3, right? It looks like it's headed to negative 3 from the left. And what about from the right? Is it headed to the same thing?
Yes, sir.
It is. So the correct answer should be negative 3. Does everyone understand that? From the picture, we see the answer is negative 3.
But what if it doesn't show that hole?
Well, the whole shouldn't matter because remember, in a limit, we're not looking at what's happening at 1, right? We don't care what's happening here. We could care less about that point. We care about coming in from the left and from the right, right? That's what we care about. But more importantly, I only showed you this to show you that there is an answer. The answer to this problem, here should be negative 3. But how the hell are we going to get that, right? We're not going to use the graph. We have to be able to do it algebraically. All right, so that's what this section is about. We only have 15 minutes. We're going to spend a lot more time on this next class. So this is a good opportunity now for us to kind of start fresh. Let me get to a blank piece of paper here. We are trying right now to figure out what the limit as x approaches 1 of x cubed minus 1 over 1 minus x is. We know the answer's negative 3, but we're going to act like we don't know that, right? The answer is negative 3, but we're going to act like we don't know. So let's imagine that this problem is presented to you. Here it is for the first time we're looking at it and starting blank slate, right? All right, first thing we do when we look at this is we try direct substitution. So if I try direct substitution, I'm just going to put direct substitution here. If I try that, I already did that. We get 0 over 0. Okay, right? That's what we get. From here on out in this class, whenever you take a limit, okay, whenever you take a limit and you get 0 over 0, I want you to think this. Bad. Okay, this is bad. And you're going to have to do some algebra, or you're going to need to do a trick, or both. Okay, but you've got to do something. All right, you've got to do something to get to the answer -3. So in looking at this, I'm going to write it down and start it over. I need somebody in this class to tell me what algebra I could possibly do that might do something here. Does anyone recognize anything here?
Could you factor the difference?
I have an idea, but I'm not sure if it's right.
Hold on. Was it Elise?
Yeah.
Did you say something or no?
Yeah, I did.
What did you say?
Factor the difference of cubes, maybe?
Difference of cubes. Does everyone realize that the numerator x cubed minus 1 is a difference of cubes? And did we look at that formula last time or no? I don't think we did. Did we? No. On your formula sheets, you should have, I think it's on the second page. Yeah, on the first reference page, the algebra reference page, there are special factoring formulas. And here you have x cubed minus y cubed. And so we can use this formula to factor the difference of cubes. Now, I'm not going to invest a bunch of time into that because that is an algebra topic, but I am going to factor it. So that factors to be x minus 1 times x squared plus x plus 1. So if you don't know how I got from here to here, this is where you make a little star, you come to my office hours, you go get tutoring, whatever it is, make sure you know how to factor a difference of cubes. Now, okay, that seems fair. I can do that, right? This is algebraically, this is a legitimate move. I can just factor the top. And then the denominator is still 1 minus x. Okay, so we've done a little bit of algebra. Did it help? Did we get anywhere? Did it allow us to do anything?
Yes.
What can we do? Do y'all see that these are almost the same? Aren't they? I mean, they're almost the same. One of them is x minus 1, the other one is 1 minus x. So don't they're off by a sign, right? It's just a sign that's off. So I'm going to do something kind of clever and tricky. I'm going to factor out a -1 from this guy right here. So just let me write this down and tell me whether or not you believe it. Hey, Elise.
Yeah.
You're the new student, right?
Yes, sir.
Okay, good. I need to put you on my little list here. After class, if you want to talk to me at all about anything, we can, okay?
All right, thank you.
Okay, do y'all agree with what I just did? I pulled a
Yes.
-1 out of here. And the reason I did that is because now if you look at this and you look at this, they're exactly the same. Now they're not in the same order, but I can simply rearrange this top one as 1 minus x, because -x plus 1 is the same as 1 minus x. And now this will cancel with this. And when I do that, what do I have left? Let's see. I still have the -1 here. And I still have this parentheses here. And now at this point, I'm going to use direct substitution, because what we've essentially done is the part that was causing the division by 0, right? That part in blue there, the 1 minus x, that was causing division by 0, and it was causing a problem. But because of our clever factoring, getting it to cancel, now I don't have division by 0. So I can just use direct substitution. And now I'm just going to replace all the x's with 1s. So I have -1. I have replaced that 1 plus 1 plus 1. And now that gives me negative 1 times 3. And hey, voila, look at that, -3. It matches what we saw graphically, doesn't it? Matches what we saw graphically. Okay. So a couple of things I want to point out on this. I just want to run through it all one more time. We started out with the original problem here in gray. We tried direct substitution. We got 0 over 0. At that point, we realized that that's bad and we have to do something. On your test, if you get 0 over 0 and tell me undefined, you are going to get no points for this problem, because this is what calculus is all about. It's not you telling me 0 over 0 is undefined. It's you now doing some algebra to be able to work the limit out to actually get an answer. All right, well, maybe I'll give you 1 point for at least doing direct substitution. Okay, so once we figured out it was bad, we wrote the original problem down, and I want you to pay attention to the fact that I wrote limit x approaches 1 every single time I went to the next step. It was there the whole time, right? Until the very last step, when I actually replaced these x's with 1s, that's when the limit goes away and you get your final answer. So this is about notation. When you're working your problems out, I expect to see limit, 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 until you actually run the limit and do the direct substitution. It's what I'm asking you to do is basically use periods and proper notation. Like if you write a paper or something, right? You have to have periods to separate your sentences. Look, this is notation. It's important. The limit needs to be there. You can't just like let it vanish and come back, and it's got to be there until you actually evaluate the limit. Okay. You happy? Not happy? Let's do another one. We have enough time for another one. Should I do that to you? We may as well just dive right in. All right, so here we go. I'm going to call on Natalie because, is Natalie here?
Yes, sir.
Okay, so Natalie, take a look at that limit. Start with direct substitution, right?
Mm-hmm.
So if you do direct substitution, replace all your x's with what?
0.
Okay, so let me write that down. Square root 0 plus 1 minus 1 over 0. What do you think, Natalie?
Since you have the 0 in the denominator, it's undefined.
Yeah, so this is, you get 0 on the top also, right?
Yeah.
You get 0 on the top and 0 on the bottom. And so what are you thinking, Natalie, when you see 0 over 0 now? This is what?
Bad.
It's bad. Okay, I know it's stupid and it's kind of childish for me to have you say that. It's bad. But I want you to remember that that's the trigger. The 0 over 0 is the thing that's going to initiate in your mind that you still have something to do, okay? You're not done. So it's bad, and Natalie, anytime we see bad, what are the things we're going to try?
Algebra or trick.
Algebra or some sort of trick or some sort of craziness, I don't know. Okay, so here we go. I'm going to rewrite the problem. Natalie's off the hook. Rewrite the problem. Now, I know that there are some of you in here who know what to do next. Okay, but I don't want you to give it away, because when you were the first time you ever saw this problem, you probably didn't think to do what you need to do. So I'm going to call on Carla, and I apologize to Carla ahead of time. Carla, are you there?
Yes, sir, I'm here.
Okay, Carla. We have a bad situation. It's 0 over 0. We've got to do some algebra, some sort of trick. So Carla, the thing that's causing the problem, Carla, is that X right there. If that X was gone, you wouldn't have division by 0. The problem is we don't have a nice, easy way of canceling the X, at least the way we're looking at it now. It doesn't appear that there's like an X up here that we can cancel with, right?
Yes.
So we need some algebra. But if you look at, I mean, there's, Carla, I mean, isn't it kind of like what do you do? I mean, do you feel kind of that way right now? Like, what in the world do I do with that?
Yes, a little bit.
Yeah.
Yes.
So is there anyone who has not seen this, who has some sort of intuition as to what we could try? We have to try something.
I would say try squaring it, maybe.
Oh, I'm glad you said that. So if you square it, if you square a square root, the square root goes away. Everyone agree?
Mm-hmm.
The problem with squaring is this. If you square, then you might be thinking, okay, I'll square the top, and whatever I do to the top, I have to do the bottom. Maybe that's what you're thinking. I don't know. You can't do that. The reason you can't do that is because this is a fraction. It's an expression. You are not free to just square top and bottom. Let me put it this way. If I give you the fraction 1/3 and you just decide to square it, top and bottom, is it the same thing or no? So square the top, square the bottom, you get 1/9. Is 1/9 equal to 1/3?
No.
They're not the same, right? 1/9 is not 1/3. So by squaring the top and bottom, you're actually changing the problem, which you're not allowed to do. I mean, we're trying to figure out what this limit is. So squaring arbitrarily the top and bottom is not possible. But it's a good, I mean, you're thinking, yeah, let's get rid of the square root, right? Let's try and get rid of the square root. Okay, so here's what we're gonna do, because we could probably sit here and look at this for the next hour and nobody get it. What we're gonna do is we're going to try and get rid of the square root, like I think Benjamin said, okay? What we're gonna do is we're gonna multiply by 1. But the one we're gonna multiply by is gonna be chosen very, very, well, we're gonna be clever. We're gonna multiply the top and bottom of this. Okay, now somebody who knows, tell us. By what?
By its conjugate.
By the conjugate. Okay, so the conjugate, what we mean is we're gonna look at this expression up here and we're gonna rewrite that expression, but we are gonna change the minus to a plus in between the two numbers. And whatever we do on the top, we must do on the bottom. Now you might be asking me or Danielle, who said that, to do the conjugate. Why? And the answer is because it's gonna frickin' work, okay? That's why. It's gonna work. And now you know that, okay? Now you know that whenever you see square roots, the conjugate is there, okay? It may work, it may not, depends on the problem, but it's one of our tricks, okay? We've got it in our arsenal now. We pull it out when we wanna try it. Here we go. So that's called the conjugate. Now watch what happens. I only have 1 minute. When I FOIL the top, I multiply that times that, the root goes away. Do you agree? So I'm ready for the next line. I have to write the limit again because I haven't actually let X go to 0. So those two go together and I get X plus 1. Now, can somebody tell me what happens in the next two multiplications, here to here and here to here? What will always happen if those are conjugates?
They cancel out.
Austin, Carlo, yes, they're going to cancel. So you actually don't even have to do the outer and the inner multiplications. The only thing that's going to matter now is the last multiplication, which is the -1 times the +1, which gives you -1. All right, so because of time, I have to finish this. That is what happens when we multiply out the top. Now, the bottom is still this X. I'm just going to leave it here. And then it's all this crap right here, which I'm actually not gonna multiply that through, and you'll see why in a second. So algebraically, is Mustafa here or no? Okay. I actually called on everybody, I believe. So if you didn't get called on, you're not on my roster for some reason, so you might want to talk to me. Do y'all see what's going to happen with the 1 and the -1 up here in the top?
Yes.
They go away. And once those two go away, do y'all see that this x that used to be a problem is now going to cancel with that x? Those two are going to cancel. And so what we have is the limit. X approaches 0. Now be real careful here. What's still in the numerator? Like everything went away, but what's still there?
0.
Not 0. When we cancel this x, we're really just reducing it to 1 over 1. So there's a 1 up here. And in the denominator, don't we have this? We never dealt with that, did we?
No.
But it's okay now. Because now the part that was causing the problem, when Carla, I think it was Carla, was talking about earlier, may not have been Carla. Yeah, it was Carla. I told Carla that x is the problem, right? The x is the problem, but we got it to cancel. So now direct substitution, no more limit. Let's replace x with 0. 1 over square root of 0 plus 1 plus 1. And we get 1 over, let's see, square root of 1 is 1, and 1 plus 1 is 2, so it's a half. The answer is a half. All right, we have just put our toes into the water here. The next class will be a bunch of us doing algebra and tricks to do limits, all right? I do not believe that you're ready for your homework for this section, which is what is it, 1-3? No, I forgot what section we're in.
I think it's 4.
Are we in 1-4? Yeah, you're not quite ready for the homework in 1-4. But I will tell you that the homework for 1-4 is one of the most important homework sections in the entire book. Like, you have to get this down in order to be able to move forward in the class. There's so much algebra in here that you need to see and be comfortable with that if you somehow just kind of wing it and skip through it, it's just going to come back to haunt you like throughout the rest of the course. So, okay, that's all we have for today. I'm sorry I went over. I'll hang out here if you have any questions. Finish your homework 1-1 through 1-3. Make sure you've done all that, and we will hit 1-4 hard on Thursday. All right. Okay, y'all have a good one.
All right.
If you have a question, just
Thank
hang on.
you.
I'm going to take this call real quick.
Okay, thank you.
Okay, what's going on? Who wants to go first?
Yeah, I was just gonna ask you, am I gonna need like a graphing calculator or anything? Because like I've just been using Desmos for the most part. I'm not sure if I'm actually gonna need like for the tests or anything.
Yeah, so during the test, you can't use a computer. So I think that you need to have something that can assist you. I'm not saying graphing calculator is not required in this course. However, it's very helpful. you know, because then you can like verify answers and things like that. You don't have a graphing calculator?
No, sir. And I mean, I'm gonna be taking Cal 2 and Cal 3 as well. Will I need it for those courses?
I think, what's your major?
Astrophysics.
Yeah, I mean, I think that you're in a field where like at some point you need to get yourself a good graphing calculator, you know, and learn how to use it and all that.
Yes,
But I
sir.
would say, you know, if you want just kind of like the run-of-the-mill graphing calculator, TI-84 is a good one, you know. I'm sure you can find some used ones.
Is that what you would recommend?
Yeah, because with graphing calculators, we have like two categories. We have ones that don't do calculus and algebra, and those are called just standard graphing calculators. TI-84 is a standard graphing calculator. Then we have ones that are called CAS, and those have what's called a computer algebra system in them, which means they can do almost everything. They can do limits, they can do, and those are awesome calculators, but a lot of schools don't let you use those on tests. So like even me, I think the syllabus says you can't use a CAS calculator on our tests. So I would say, to be safe, TI-84 is a relatively inexpensive calculator because you can find them used. That would get the job done. Yeah.
Okay, that works.
All right.
So is this
What do you have there? Is that the 84?
Yes, it's
84 plus?
TI-84 plus CE.
Yeah. Okay. So that's like a really fancy one because does it color? Is that in color? No?
Yes.
Yeah.
More
So
likely.
there's different levels of the 84 because the 84, you know, there's like a basic one, right? Black and white basically, but the brains and the functionality is the same in all of them. It's just how fancy it is as far as the user interface. So
I just got it on a deal, so it was.
So really just any TI-84 is what I need.
yeah, you can do an 84, you can do, I don't even know if they sell 85 or 86 anymore, but you know. What you want to avoid is the 89, the TI-89, and you want to avoid the TI-Nspire CAS. Because there's an Nspire. Okay, this is a TI-83. This is like old school. This would be fine, okay? Because it graphs. I mean, this is the Nspire. It's dead right now. I mean, charge batteries. This is the Nspire, which is color, but it's not the CAS. It would say up on the top CAS if it had the computer algebra system. This one does not. So stay away from the 89 and the TI Nspire CAS, and I think you'll be fine. Now, down the road, you know, like after you get through most of your math courses, I would encourage you to get one with the computer algebra system. Like I have the 89 here. This is the 89, and this does everything. The limit we just did, I could do it on my calculator. So it's a good thing to have down the road, the ability to do that. But again, for testing purposes, most schools aren't going to let you use that one.
Okay, that's all I needed to know. Thank you.
Okay. Dilpreet, do you have a question?
Yes. So I kind of don't understand how were you be able to see that answer -3 for the example we did last one. This one.
Like, you don't.
I mean, how did you just like looking at the graph? How did you say it's -3?
Oh,
even
off
if
the
it wasn't
graph.
any point or anything.
No, we do have a point. The limit was the limit as x approaches 1.
Right.
So we go to here's x is 1, right?
Right. I get that, but where do you get that 3 from though?
-3.
Yeah, right. But you don't really have a graph like. Oh, okay. Never mind. It was me. I was just overthinking.
And we do have a hole here, but we do approach -3 from both
Negative
sides. Okay.
Yeah, actually, I did not see that -3 before. I was thinking, I was only looking at a graph, but not as a limit though. As
Okay.
like a regular graph as we think in algebra. Okay, this is a negative infinity.
Okay. Gotcha. But it makes sense now? You're okay? Okay. All right. Elise, do you have a question? Welcome to the class. Elise, did you get, am I saying your name right? Elise?
Yeah, you are.
Okay.
Really common.
So, yeah, so you're joining in late, right? But have you been able to get like caught up with things?
Yeah, I remember learning this, like I said before.
I can barely hear you.
I've actually taken a calc class before. I'm trying to put earphones in.
She said she has taken calc class before, so she kind of knows what we're doing.
Yeah, yeah. I'm just saying as far as like getting into our like main page where I put everything for everyone, were you able to get to here and stuff? Okay, so wait a minute, this doesn't look like it. Is that it? Wrong semester. So this is what it looks like. And so the class lectures, that's what I'm, if you want to go back and look at what I've done, you can watch that video. Now I forgot to record the very first day. I thought it was a recording, but it wasn't. So yeah. But yeah, I mean, I just want to be able to answer any questions if you have any about the expectations, what, like how homework works, how exams work or anything.
Yeah, how does the homework work? Is it like we do it ourselves or we have to submit a photo or anything?
The exams or the homework?
Homework.
You're like frozen on, okay, there, now you're back. I don't know if it's my internet or yours.
I've been freezing up throughout the class.
Okay, so were you asking about the homework or exams?
The homework.
Homework. Okay, so all you're doing is you're going to this link to WebAssign, and you're just going to open up you're going to register, and then so the registration is just all you have to do is copy this course key right there, that class key. Just copy it, and then come over here and enter it into here. Well, and you'll get registered. All right. Do you think you can do that? Dilpreet, can you hear her?
No, sir.
Yeah. Yeah.
I think we could hear you without your headphones.
Yeah. It's just not.
I tried signing in earlier, but I think I used the wrong code.
Okay. Okay.
You did.
Once you get in there though, that's where you get to the ebook, and you're doing the homework on your own. I don't collect it. You don't submit it online. And that's because I've already given you all the homework solutions. If you just look at these videos, I've already worked out all the problems. So the idea is that when you do the homework, you can check with my answers to see if we're getting the same thing, if you're going about it the right way, right? So here's me just working through all the homework problems for this section. So it's just practice, that's all it is, okay?
Okay.
And then the exams, that'll be where I send you the exam, and you're gonna do the exam live on Zoom with the rest of the class. And when we get to that, I'll explain a little more.
All right.
Yeah.
Last question that I have is, I have the 8th edition of the book that we're using.
Oh, you do have the book?
I have the 8th edition. I have the 8th.
I don't know if there is an 8th edition to this.
Let me pull up the exact name.
You should be able to find this online for free, but that's what the access to the website gives you. If you go in here, it gives you, you can get to the ebook, and that's where you can do the homework. So, let's see. So when you go in here as a student, it looks like this. And there's no assignments or anything here. All you do is just click on the ebook. And you go to whatever section it is to do the homework. And then like here are the exercises, and then you can get, you know, look at the different pages. So your first assignment is on the schedule for the class. I have the schedule here. Have you looked at that yet?
No.
Okay, so if you look at that schedule, I would just download this and print it. It shows you for each section what problems to do. So that means you go to that ebook and you're supposed to do, out of 1.1, you're supposed to do 2, 3, 4, 20. So you're supposed to do number 2, number 3, number 4, and you just do those on paper on the side, you know. Does that make sense or not?
It does.
Okay, and did I put an orientation video? I did not, okay. I can send you, let me send it in the chat. See if I can find it real quick. Did you get an email from me with a, like, welcome to this class? It would have, I doubt it because you came in late. Let me see here, it's right here. Let me share it. Okay, I'm gonna put it in the chat for you. So if you, there it goes. There it goes. So if you click on that link, it's just a very short, like 15-minute video of me explaining to the class like how everything works. So that went out like the day or two before classes started. So I think that'll help you kind of get a feel for what's expected and stuff.
It's 5-minute video though.
Is
It's
it
only
5?
5 minutes. Yeah.
Did I really blow through it that fast? Okay, I guess
Yes,
I was in a hurry.
it was only 5 minutes.
Yeah. So if you have any questions, at all, just contact me. My cell phone number is on the syllabus. So if you go to the course syllabus, my cell phone number is here. And you can just text me or call me if you have any questions. All right.
Hey, Professor, will we be able to use the formula sheet on the exam?
Yes, you can use, for the exam, you can have all the formula sheets under files. So if you go to files, you go to formulas, you can have these, I think it's 6 pages. Yeah.
Okay, got it. And also, Professor, did you get my accommodation letter?
I did.
Okay, great.
Now, I'll be honest with you, I just breezed through it, but I'm assuming you get extra time. And that's
Pretty
the main
much.
thing. Is
The
that the
only
main
thing
thing?
is, yeah, that's pretty much, I guess. And some professors do, but I'm not expecting anything from this class. Like I do know I do have to learn these things no matter what, right? So I'm not expecting to use any notes or anything.
Yeah.
So we're good there.
Okay.
The only thing for today, I just wanted to know the factorization you did on the cubic. Is there
Mhm.
any way you can just tell me how to do it? I mean, I probably know, but I have forgotten it.
So this is the factoring right here. So
Mhm.
all I'm doing is using the formula that says this. If you have x cubed, x cubed minus y cubed, it'll be x minus y times x squared plus x times y plus y squared. And that's on your formula sheets.
Okay, got it. Okay.
And so in this particular case, for us, the x is actually x, right?
Mhm.
And the y is actually 1,
Mhm.
right? So we're just going to go x minus 1, x squared plus x times
it.
1, which is that, and then 1 squared.
Got it. Okay. And Professor, with me, the only thing is I just kind of, whenever, you ask me a question, okay, what's that? It's just like, I'm blank. Like, what do you have asked me? I just kind of freak out. It's just me. It's related to my anxiety.
Don't worry about it.
I try to give the right answer, but no,
Don't worry
It-
about it. I mean,
it
it's,
doesn't work.
this
I
is
apologize.
not,
I mean, I do know what we are doing. I can like literally sit and tell. But whenever somebody asks me, it just like, okay, I'm blank. Just don't ask me. I'm just freaking out. But
well,
I
I
know
mean,
like what I'm doing.
yeah, I mean, it's not part of your grade. I mean, it's just, I only call on all of you because I want to keep the class somewhat engaging, you know, like engaged. And I want you to be sitting there like wondering if you're next to get picked, you know?
Right.
It
It's
keeps
totally
you
fine with me.
paying
I
attention.
really like that idea though.
Yeah.
Like debate.
Don't worry about it.
But I apologize. Like
No,
I'm
don't.
just literally fighting with my mind, like what I'm supposed to do right now. So I just say whatever it just comes in my mind.
Yeah, don't worry about it. It's, I mean, no, everyone's gonna leave the class and go on with their lives. No one's gonna care who answers what, you know? It is what it is.
Right.
So,
Right. But I really apologize. I'm very sorry, but I'm pretty sure I'll do well on the test though.
okay, yeah, well. All right, I've got to run. I've got somewhere to be. It's 3 o'clock, so
Yes, sir. You have a nice day.
you too.
Thank
Thanks.
you.